All right, so welcome to the final day of our talent course on machine learning for nuclear physics this year. We're going to round off the summer school this year by taking a brief tour of the subfield of reinforcement learning, which is one of the subfields of machine learning. So for the majority of our time together over these last couple of weeks, we've discussed supervised learning. So that's the setting where you're given a data set where you have inputs and outputs, and the goal is to learn some function that maps your inputs to your outputs, right? So it's essentially an exercise in curve fitting. Yesterday, Michelle provided an overview of some topics from unsupervised learning. So this is a setting where the problem you're given is simply the data set you're given only has inputs. So there's no outputs per se, right? So there's no labels. And the task is maybe a little more vague, where you're just given a data set and the task is tell me something interesting about this data. So that could be clustering the data together. It could be find a lower dimensional encoding of the same data, or it could be some kind of generative modeling where the goal is to model the distribution of your data so that you can then sample new data points from that data set. So kind of what a GAN does. Reinforcement learning, in contrast, is a different problem setting compared to those. Here, we're really talking about so-called sequential decision problems. So you can imagine that an agent gets dropped off in some environment, so some kind of alien planet, and then it has no prior knowledge about the rules in this world, right? About the dynamics of the world. And its goal is to essentially maximize its well-being, if we think about it informally. So it needs to survive and flourish in this environment, and the environment will provide periodic feedback, right? So the main difference is from the supervised learning setting is you now don't get to make just one prediction, you make a whole sequence of actions. And the feedback you receive, so with supervised learning, for every prediction I make, I can instantly compare it to the true label. But in reinforcement learning, the feedback is not necessarily immediate. It may be delayed for quite a bit. So I may have to make tens, hundreds of actions before I get any meaningful feedback. So the feedback is sparse. And it may be delayed as well. So there may be quite a bit of time may elapse between when I do something and when I find out what impact that action had. And the general learning problem then is, how do you figure out how to behave optimally in this environment? So how do you figure out how to flourish in this environment? So there's been a resurgence of interest in reinforcement learning again since around 2014 or so, and that actually coincides with a pretty famous paper out of DeepMind, right? So this is really the paper that put them on everyone's radar. It's what led to the $500 million Google takeover, this single publication, where they demoed a system that was able to use reinforcement learning techniques in combination with deep neural networks. So what they call deep reinforcement learning, so deep RL. And they used it to build a system that, using a same algorithm and a fixed network architecture, could start from a random policy. So just randomly play games and figure out how to get to a superhuman level in dozens of classic Atari video games. So initially it's just pushing your buttons at random, and then through this process of trial and error, it got to a place where it was consistently beating human level performance across a wide variety of games. And the impressive thing was that it started from scratch, and that the same algorithm was able to repeat its success in a number of different domains. And of course, this was followed up by the even more high-profile success, which was front-page news all across the world when Google's AlphaGo and later AlphaZero systems were able to start crushing humans at board games, right? So they were able to learn from scratch and beat the best humans at chess, and more famously, the game of Go, which was for decades considered sort of the final frontier in AI planning. So my PhD thesis, for example, was focused on Go-playing algorithms. And I remember when I finished handing in my thesis, the general thinking was success in Go was still maybe a few decades away. It ended up being more like 3 or 4 years. And increasingly, we're starting to see these deep RL techniques filter out into sort of wider applications. So robotics is maybe the other one where there's been a real impact. So in terms of coming up with algorithms for grasping novel objects and manipulating them and things like that. Increasingly, we're also seeing this in scientific discovery, in things like fluid mechanics, in drug discovery, and people are starting to investigate these techniques in nuclear physics as well. So Michelle and I are in the very early stages of embarking on one of these projects, for example. Question in the chat, did human chess get beaten first? Yes, chess by decades, as one person pointed out. So the famous matchup between Deep Blue and Garry Kasparov, that was in the mid-90s. Go, in contrast, I believe was 2016, maybe 2015, 2016. And what is reinforced here, like in reinforcing concrete, so what is reinforced here is good behavior. So it's kind of like if you were to train a dog. So when the dog does something that you approve of, you give it a treat, and when it behaves badly, you scold it, I guess. So that's essentially what is being reinforced, right? It's much the same concept. You have a system that's taking a bunch of actions, and you want to encourage good behavior and discourage bad actions. Right. So it is some sort of schedule of reward and punishment. Yes, that's one way to think about it. So to begin with, we're going to work our way through some formalism, so understand how we model these sequential decision problems. And once we have sort of a theoretical framework to talk about these problems, we'll look at some algorithms for how we go about approaching and modeling these problems. So a good place to start is this notion of a Markov chain. Best may be understood via an example. So let's just start with an example of a Markov chain, and then we'll take our intuitions and formalize them with some mathematics, right? So you can think of a Markov chain as essentially a finite state machine. So you have a collection of states. So in this case, what I'm going to be modeling is maybe the career of, say, an academic. So you find yourself at the bottom of the academic ladder as an assistant professor. So this is a state your system can be in, right? And every state has an associated reward. So this is the immediate reward of being in this state. So I guess I wasn't specific about the time scale, but let's say this is how much you get for a year, I guess. So you get some immediate reward. And what happens next is that your system transitions, right? So your system evolves over time. So on each time step, you flip a coin, and according to a probability distribution, you end up in another state in your system. So in this case, there is a 20% probability, 20% chance that you transition on the next time step to getting tenure, I guess, and becoming an associate professor. And here is the reward associated with this new state, right? Of course, your transition probabilities need to sum to 1. So this is clearly just one of possible transitions that could happen. Let's say there is a 0.6 probability that at the end of the year, you just stay in your current position. And for the remaining probability mass, we'll say, oh, okay, so maybe there's some burnout and you find yourself joining some hot deep learning startup, right? For a pretty significant pay bump. So this is essentially what a Markov chain is, right? So your system can be described using some descriptor. So you find yourself in some state, you collect a reward, and then nature happens, right? So you flip a coin, and then you transition into another state. The one thing to note here is our agent. So this poor person has really no agency, right? So they don't get to control events in any way. They have no influence over the state transitions. They simply just go with the flow. So they're just dropped in this environment and you get buffeted by the winds of change and you just kind of end up in other places. And not autobiographical. So there's a question in the chat about that. So we just go through this and we can just simulate this chain for a while, right? So to fill this out, we can go through and sort of add more states. So for every state, there's going to be some transitions, and at some point, I guess you retire to the beach. So this, in a nutshell, is a Markov chain. So one important thing to note about the system is the so-called Markovian property. So what that means is that the path I take through the system doesn't really matter, right? Quick question, what is the self-coupling? So these self arrows are simply mean that when I flip the coin, my system just stayed in the same state, right? So I did not transition to a different state. So you can have self edges. So this system has what's called the Markovian property, meaning if the history of how I got to a state doesn't matter. So once I get to a state like this one, to figure out what will happen in the future, I simply have to look at the distribution across the transitions that lead out, and that alone influences what will happen to me in the future, right? So in some sense, once I've made it to this state, it doesn't matter how I got there. Well, maybe a better example is this one. Once I make it to this state, notice there are two paths. And the Markovian property says you don't have to remember your history. Once you've made it here, you've made it there. So the evolution of your system into the future simply depends on where you are right now, right? So what are some questions we can ask about the system? So typically the most interesting thing about the system, or the thing we're interested in most, is the notion of the value of a state, right? So the value or the utility of a state. So contrast this with what I call the immediate reward earlier. So the immediate reward refers to the fact that if I find myself in this state, I get 10K right away, right? The value, on the other hand, encapsulates sort of long-term payoff. So in other words, if I were to start in this state and then I just simulate this chain for a very long amount of time, right? So an infinite number of time steps. So I just start here and start my simulation, flip coins, and just start transitioning through the edges according to the probabilities listed there. How much reward will I accrue in the long run, right? That is essentially what this value function is capturing. So the value of a state is the long-term reward that gets accrued. Couple of questions in the chat. Is self-coupling probability always higher? No, I mean, the numbers are just made up. I just picked things out of a hat. So you may not even have necessarily solved loops. That's really just a function of the domain you're working in. Where is the punishment part? Well, maybe this is your punishment, right? That your reward's only that compared to, say, higher ranks. But essentially the numbers are the punishment. So you could imagine that there are states where, you know, the reward could be negative. So there's nothing saying that the reward has to be a positive number. So what we're typically interested in then is a question we like to ask is, what is the utility of a given state? So let's, for example, try to figure out what the utility of this state A is, right? So we can write it out. So V of A would simply be, what do I collect in this state? So that's 10K. And then if I start simulating my chain, what can happen is, well, I could end up in this state after one coin flip. So I would get another 50K. And then maybe I flip the coin again and I stay there. And then I flip the coin and I stay there. And we just keep going, right? Of course, this is calculated based on one particular trajectory. So in principle, what we'd have to do is average over all possible trajectories, right? So we'll derive an expression for that in a second. So one way to estimate this would be simply doing a simulation. So do this over and over and average over all possible trajectories. But one thing about the summation you'll notice, right, is, well, if I keep adding and I'm doing an infinite summation, well, hey, I make an infinite amount of money, which is a nice thought, but it's probably not going to happen, right? So the common sort of solution to this problem in economics, in many other disciplines, is to add a discount factor. So to model the idea that $1 earned tomorrow should be worth less than $1 I get right away today, payoffs in the future typically get discounted, and they get discounted exponentially. So what we would do then is, for future payoffs, we would multiply them by some factor gamma, and we would discount them exponentially, right? So this is kind of like compound interest, if you will. So this gamma term is usually just some real number in this interval. So it's some number smaller than 1, so which means that every time you do these multiplications, these are getting smaller. So 50K tomorrow is not truly worth 50K today, but it's worth a little less today, right? And the further into the future you go, the more heavily you discount, right? Because as you cube and take higher powers of these numbers, this multiplicative factor becomes smaller and smaller, so it devalues this more and more in today's terms, right? So that's the first major adjustment we have to make to the scheme. So we're going to discount our future rewards. So the value function in that case is essentially, once we have discounting in place, we can define it more precisely. It refers to the expected sum of your discounted future rewards, right? So in other words, run this chain forever and sum up, average over all potential trajectories you could see, the payoffs you could get, while making sure to discount them. So question in the chat, is it sort of an infinite series? Yes, it will be, right? But the fact that we're discounting means that the sum of that infinite series is going to stay bounded. So it's not going to be, it's not going to diverge, right? So let's actually, now that we have that definition in place, let's actually try to maybe define this a little more formally, right? So V of A then is clearly the sum of the immediate reward, which is 10K in this case. And then to capture this idea of average over all possible future trajectories, we can take an expectation over what's going to happen in the future. So that's simply the summation of the future states I could find myself in, weighted by the probability that I end up in those states, right? So that's just the definition of the expectation of a random variable. So in this case, and remember, we'll also discount. So discount, and oh, actually, I did not mean to, so we'll just scratch that. So let's think about this. So the discounted sum of each of the values of the future states I could find myself in, weighted by their probabilities. So what we're going to end up with is a recursive equation here. So V of A, if I start in V of A, so what is the value of this state? So there's some immediate reward, and then there's a 60% chance I find myself back here again tomorrow, right? Which means I should weigh that outcome by the probability 0.6. And then what is the value associated with that outcome? Well, if I find myself back in state A again, then if I spin out that future, then I should multiply this basically by V of A again, right? So I collect an immediate reward, and then this term encodes my potential future earnings, right? My future earnings weighted by the probability that I find myself in that scenario. But of course, this is only one of 3 things that could happen to me. So another thing that could happen to me is I transition to this state. There's a 0.2 probability that that happens, in which case this encodes my future earnings. And finally, there's a point to probability I end up in this state, in which case V of D encodes my future earnings. So what we've in effect set up is, notice that a bunch of the things here we already know. So gamma is just some number we pick. It's just the discount factor we choose to use. So this is just a scalar. And what we have is essentially a linear equation, right? So the V's are the things we don't know and the things we would like to solve for in the system. And what we have instead is one linear equation that relates the value of A to the values of its neighbors. And if we repeated this exercise and came up with an equation for V of B, we could repeat the same analysis. We'd have a similar looking equation for V of B, similar one for C, D, and E. So when you were done, you would simply have 5 equations and 5 variables, right? So that's simply a system of linear equations. Well, solving that, we have standard linear algebra tools to solve that. So solving a system of linear equations is straightforward. So we can just plug it into your favorite linear algebra solver. I mean, in this example, we can even just do this by hand, right? And you would have the analytical solution for each of these estimates, for each of these valuations. So that is sort of the intuitive view of what a Markov chain is and how you solve for the values. So question in the chat. So the equation for V of E is simply 10K plus that. Yes, that is correct. The only thing you're missing there is the discount factor. So it would actually be gamma times the reward, right? So let's set up the equation for V of E. This is 10K plus gamma times V of E. Oh, that's what you meant when you wrote R. Sorry, that was the gamma, my bad. Yes, that is the equation. So the equation for V of E is actually just an equation in one variable. But once we've solved for this one, we can start plugging it back into the other equations to start solving for the other variables. Right. So let's take this idea and generalize it, right? So if we formalize it, then to define any Markov chain, it seems like we just need to define a few things. So we need a set of states. So these are the bubbles from the previous picture. So in a finite Markov chain, you only have, say, n states, so one bubble per state. You have a transition matrix, which we'll denote by P, right? And this is essentially one compact way of representing the probabilities on all of those arrows. So each entry in this matrix, so Pij, is going to give me the probability that I find myself in state Sj on the next time step, given that I'm currently in state Si. Right, so this is those probabilities will be associated with every edge. So the Ij entry here is the probability associated with the edge that goes from node Si to node Sj. R is simply the reward function. So this is the numbers we had in each of the states. So for every state, it simply needs to give you some real number telling you what the immediate reward of being in that state is. And gamma we already discussed, right? So this is simply the discount factor. So if I give you these 4 things, I have effectively defined a Markov chain for you. And this exercise we went through of setting up the linear equations, we can quickly do that here as well, right? So, but we can do it in a vectorized form, so we can make it a little more compact. Could gamma be a matrix? Not really. So gamma is a scalar, right? So typically, we just use a fixed discount rate across the entire system. So you could, I suppose, in principle, choose a different discount factor for different parts of your system, but that's typically not done because, I mean, that becomes a harder formalism to work with. So typically, this is just a scalar. Okay, so if we vectorize things, so you can imagine a column vector that gives me the values of all my states. And similarly, you could imagine a column vector of my rewards, which, oops, which simply arranges the rewards of all my states. So once we do that, the linear system we were solving a second ago, we can set it up in a pretty straightforward fashion using this formalism, right? So the value function basically just takes the immediate reward, and then you take the discounted sum of the future rewards, right? So gamma times, you multiply the probability matrix by V again. So if you think about it, so why does this product work? So if this is my matrix P, so if we take the first row of this matrix, these are all the probabilities of the transitions that could happen out of state one. So I would take this row and multiply it by these, and that makes sense, right? So P11 would get multiplied by the value of S1. So the probability of starting in state one and ending in state one gets multiplied by the value of state one. And then the probability of starting in state one and transitioning to two would get multiplied by the value of state two, and so on, right? So which is exactly the form of the equation we just saw a second ago. Of course, some of these entries could be zero, in which case we just knock it out when we were multiplying and summing them together when performing this product, right? And once we have this linear system, well, solving it is straightforward, right? So just do a little bit of algebra here. So I can move this term over to the other side and collect like things together. So we end up with that. And since V is the thing we want to solve for, if we pre-multiply by the inverse of that matrix, we end up there. So again, plug this into your favorite linear algebra solver, and you're off to the races, right? So you can solve for V directly. Couple of questions in the chat. So once we leave a state, we cannot return to it. Is that true in general? Not true in general, right? So you don't want to take that example and take it too literally. So as Chiranjit points out, you can, it really depends on the structure of your transition matrix. So for every entry like 2, 1, there's going to be a symmetric entry that's a 1, 2, right? So basically, if you want a non-zero probability of leaving a state and returning to it, you just want to make sure that both of these are non-zero. So you can always come back someplace you left. Oh, yes, there should be an R. Thank you. If Pij is the leaving the state probability, Pji should be returning to the state. Correct. But there is nothing requiring this matrix to be symmetric in that way. So that's really system dependent. So could the diagonal terms give us the probability of self-interaction? Yes, that's exactly what the diagonal terms are. The probability of staying in the same state. I don't know what a mesonic system is, but maybe one of the physicists can confirm, can help answer that. Gamma is a parameter we find. Yeah, so I mean, this is a free parameter, right? So a priori, the system doesn't necessarily tell you what to set that to. It's whatever seems appropriate, right? So typically in most applications, at least in reinforcement learning, I've seldom seen a discount factor outside the range. It's actually a much narrower range than 0 to 1. It's typically something between 0.9 and 0.999 even, right? So something in this range is typically what I've seen used in most reinforcement learning algorithms. Okay, so matrix inversion can be expensive, right? So we need to compute this matrix and invert it. So depending on how big this transition matrix is, while this will give you the analytic solution for the values, this can get expensive, right? So oftentimes there is a different way of solving for the value function, an algorithm known as value iteration. So rather than try to invert this matrix, we can try to successively come up with approximations to this value function and try to converge to this true value function via a series of approximations. So this requires setting up a series of approximations, like I said, right? So we'll define, so remember, we're trying to find what I'll denote as V star, so the true value function, so the true value of every state. And we'll get to this optimal value function by making a series of k-step approximations. So what do I mean by that? So V0, so remember, V star is the payoff I get if I start in state S and I run my chain forever. So rather than estimate that using a single step computation, let me get there in a bunch of baby steps. So what I'm going to start with is an estimate of V0, which is if I start in state Si and I run my chain for 0 steps, then what's the value of the state Si? And this one is actually really easy to compute, right? So if I just start in a state and then I don't run my chain at all, then the only reward I get is the immediate reward I got for being in that state and nothing more. So V0, and again, I'm going to compress the notation to use vectors, is simply the immediate reward, right? So for any state, the 0-step reward is simply just the immediate reward for being in that state. And now we can bootstrap from that. So if I have the 0-step reward, can I compute the 1-step reward? So if I start in a state and I run my simulation for 1 step, can I figure out what the value of every state is? And here's what we can do. So the 1-step reward involves taking whatever immediate reward the system gives you, and now the discounted sum of future rewards, right? But in this case, it's not going to be this infinite sum, but simply just a 1-step simulation that's left, right? So to perform a 1-step simulation, collect an immediate reward, and then you have a 0-step simulation left to go. So we can express this recursively. So weigh all possible states you could end up in, take their values, and you multiply by the probability of transitioning to each of those states, right? So if I start by computing this, then I can use the result of that to compute this, right? So how do we prove this is stable? So I will get to that in a minute. But let's just finish this thought, right? So we can do the same thing again. So similarly, V2 is going to be that, right? So to get a 2-step estimate, take the immediate reward, so that accounts for 1 step. And then for the remainder of your simulation, use the values you computed on the previous step. And we can just keep doing this for a while, right? So until we're satisfied that we have converged. So the convergence criterion in this case is going to be that expression, which is a bit of a mouthful, right? But it's really saying something fairly straightforward. So take 2 of these vectors that are sort of 2 steps apart, that are 1 step apart, right? So you have some vk vector from the current iteration, and then you have vk plus 1, that vk plus 1. So you update this to create that. Now, when you go from vk to vk plus 1, what I can do is look at every component in this vector and the corresponding components in this vector, and now pick out the component that changed the most. So when I did this update, which state's value changed the biggest? And if that change is below some tolerance that we are satisfied with, then we're going to call it a day, right? That's essentially what this math is saying. So we can just perform the sequence of value function approximations until this convergence criterion is met, and we call it a day. And going back to Ocean's question, will this converge? I'm going to claim without proof that it does. If we wanted to prove it, that might take up all the rest of the time we have, but it involves some results from topology. You can look up what is it called? It is a fixed point theorem. The contraction mapping theorem. So this is a pretty central result in topology, but it basically, the argument boils down to saying that every time we perform this update, we bring these 2 points closer together. or sorry, not these 2 points, we bring these 2 points closer together, right? So as you go to higher and higher Ks, the claim is that you will converge on V star. So that is the hand-wavy 10-second version of that proof, right? But if you are curious, I'm sure there are plenty of online sort of resources that will probably walk you through the theorem. Value of matrix P changes in every step? No, it does not, right? So we assume that the system is stationary. So in the sense, what that means is that your probabilities are not changing from, so the system dynamics are fixed. What changes is our estimated values of each state, because we are coming up with better and better approximations. So why might this be better than matrix inversion? Because at the end of the day, we're still performing a matrix multiplication when computing these updates, and that is just as expensive as inverting a matrix from a computational complexity standpoint. The reason this may be preferable is because in systems where your transition matrix P is sparse, meaning from each state, there's only a handful of other states I could transition to. So when that's the case, you can perform this multiplication fairly quickly, right? So if every row in my transition matrix only has like 3 or 4 non-zero entries, then I don't actually have to multiply the entire row by the entire column. I only need to multiply the non-zero values. So this multiplication can proceed very quickly, right? So especially if you have a sparse system where each state is only connected to a handful of other states, value iteration will get you there much quicker, whereas matrix inversion may simply not even be feasible, right? So, so those are a couple different approaches for solving for the value function in a Markov chain, right? But let's revisit a key simplifying assumption we made when we started all this, which was that our agent really has no agency, right? So it just gets dropped in the system and nature does its thing, and you just find yourself in all these states with no control over what's happening around you. Of course, that's not really the problem we want to study, right? The problem we want to study is, well, what if the agent does have control? What if the agent can take actions and actually influence the system, influence how the system evolves? So once we add agent decision making into the mix, we have to change our formalism a little bit, so we get what is known as a Markov decision process. So a generalization of a Markov chain, right? Yeah, I guess even I didn't really notice my background was contour lines, but yeah, somehow seems apt for a class that's heavily depends on gradient optimization. Markov decision processes. So you will recognize that this looks fairly similar to a Markov chain, but we have some additional things here. Right? So a couple of things have changed from the 4 tuple we used to define a Markov chain. In particular, we now have actions, right? So a Markov decision process, an MDP, allows your agent to take actions. So let's assume that in every state, the agent has, say, M decisions to choose from. So, so we now include that in our problem formalization. And the transition matrix, which was this matrix with entries Pij, right, in a Markov chain, it's now going to become a rank 3 tensor. So it's now indexed not just by I and j, but also by A, which is the action the agent chooses to take, right? So essentially, you now have a 3D, a rank 3 tensor, like I said, and every entry is going to say something like this. So if I find myself in some state Si, and my agent performs the action A, then what is the probability that you end up in Sj? So this conditional probability, right? So it's going to be this 3D array instead of a 2D array, right? Because you need to specify 3 things to get out a probability. And the other 3 things are just as before, right? So S is the set of states, R is the reward function, gamma is the discount factor. And this defines a Markov decision process, right? So much like we did with the Markov chain, let's now work through an example, right? So it will really help make some of these things a little less abstract and maybe help crystallize some of these ideas. So example of a Markov decision process. This is now maybe a Markov decision process modeling maybe a college student's weekend decision-making plans, right? So our hero finds themselves on a Friday evening. So that's the state. And the immediate reward for being in this state is just a 0. So you're feeling pretty neutral, right? And let's say that the action choices for our hero are, you can either go to a party, right? So it is the weekend, or you can do your homework, right? So you have 2 action choices in this state, and our actions have consequences, but they are non-deterministic, right? So if the student chooses to go to a party, yes, that's true. So maybe not entirely appropriate for the current moment in time we find ourselves in. So no, so the payoffs do not reflect current conditions on the ground. So sometime in the good old days when this sort of decision making was actually like possible. So you can choose to go to the party, in which case, if you choose that action, the actions don't necessarily have deterministic effects. So in this particular example, I'm choosing that there's a 0.7 probability that you transition to this state where you wake up happy on a Saturday morning because, hey, the party was awesome and you had a great time. But there's maybe a 0.3 probability that you wake up on Saturday with, I don't know, maybe a hangover, or you got into a fight, or whatever it may be, right? So not a fun party. And the other option is, well, do your homework, right, on a Friday night. And again, non-deterministic outcomes. So I can pick the action, and then nature decides to flip a coin, right? So maybe there's a 0.5 chance I end up waking up happy and virtuous on a Saturday morning. Look at me doing homework on a Friday. Or you wake up Saturday morning unhappy because you found out that, hey, the party was amazing and you missed out on this, I don't know. You just missed out on a great party, right? So that's essentially what the new transition matrix looks like, right? So you need to encode all of this in your tensor. So for every action in every state, it gives you some distribution over what your successive states could be, right? And we'd have to fill this out for all the other states, just like before. So this would be the complete picture of our Markov decision process, right? So in every state, you have the actions available to you, and the transitions take you to other states in your system. So in this setting, right, what we really care about, the problem we want to solve now is, how should the student think about making decisions, right? So what is the optimal way to behave in the system so that you don't want to be too short-sighted, right? So this is sort of general life advice. So how should you trade off sort of short-term gain for long-term payoff? So how do you balance that? And how do you maximize long-term well-being, if you will? Yeah, so a line goes back from Saturday. So yeah, so this is where I guess the system kind of breaks down, or the example kind of breaks down. But yeah, you imagine that, yeah, Friday is probably Friday of next week, is probably the one way to interpret that. So we're trying to come up with a life philosophy for the student, right? Or in Markov decision process speak, what we're looking for is what is called a policy. So this is a function that prescribes for every state in your system what your agent should do, right? So if you find yourself in state S1, here's what you do. In state S2, here's what you do. So think of it as this giant lookup table, which simply maps every state in your system to an action to perform in that system. And we're not searching for just any policy, right? We are searching for what we will call the optimal policy. So among all the policies, this is the one that maximizes the expected sum or discounted future rewards. So in other words, maximizes my agent's future well-being, right? So take all those rewards, sum them up over all future possible trajectories, discount them appropriately. What do I do to maximize that quantity? And to solve for this optimal policy at a very high level, here's what we're going to do. We are going to solve for the optimal value function again for the system. So we'll figure out how to value each of our states in this MDP. And then once we've solved for this, once we know the true value of every state, it'll be straightforward to extract the policy from that. Right? So that's what we're going for. Right? So again, going back, it will be helpful to keep this example in mind just so we come up, as we try to come up with an equation in this case for the value function. So let me maybe call this state SI. So again, for this optimal value function, the setup is going to be very similar to the Markov chain case, right? The only complication is the fact that we now have to take actions into account. But let's start and set it up similarly to the Markov chain and then worry about what to do about the action next. So the long-term utility of being in the state is the sum of the immediate reward and then some discounted sum of future rewards, right? So that. So this was the equation we had for the Markov chain case. So take the immediate reward for this state and then take the discounted expectation of what I can expect to earn in all my successive states. So the Pij means sum over all the states j that I could find myself in when I leave state I, scaled by the value of that successive state j, right? And of course, the complication now is that we also have this index A, right? And we haven't said what to do about that action. How do we account for that in this recursive equation? So in the chat, so someone just mentioned, why are we not summing over the actions or average? So if you think about it, yes, we do need to account for the action, but summing over the actions doesn't make any sense, right? Because if you think about it, the agent has to commit to one of these actions. You find yourself in this state, you're either going to do this or you're going to do that, right? So we need to actually choose between these, so you can't average over them. So if you average over them, then we're back in the Markov chain situation, because that's essentially kind of giving up and saying, well, I'll just randomly choose to do one of these things, right? So instead, we need to choose among these. And if we're talking about a rational agent, then the rational way to make that choice is to pick the better action, right? You're going to pick the best of these actions. And the way to say that in math would basically be to say, well, maximize over all the possible actions, right? So we would have a max operator here that chooses the best of the actions available to us. Does that make sense? So question in the chat, and I think a couple of people have already clarified it. Yes, the numbers on these arrows are the elements of our transition matrix T. So those are different from gamma. So gamma is just one number for the whole system. Question in the chat, is this algorithm just binary? Not sure I quite understand what you mean by binary. Could you expand on what you're referring to being binary? Oh, more than two decisions. Oh, there's nothing here that, I mean, this picture gets way more messy if I add more actions, right? So that's just simplifying for the case of this example. But this equation we've come up with is much more general, right? Nothing says I can't have like 20 actions and I can still take the max over 20 actions, right? So this equation, in fact, is central to everything we're about to do next, right? It's so important it even has a name. This is the Bellman equation, right? So named for Richard Bellman, who studied these problems in the 60s. And in many ways, this forms maybe the most central theoretical equation in all of reinforcement learning. And we'll look at a few variants of the form of this equation, but this is an important thing to know, right? Can we repeat why we write max of A? So the max is accounting for the fact that, so initially I didn't have the max here, right? But that would leave the action as a free variable, but we need to have something for this A, right? And what I suggested was, well, if you think about what we do at a state, a rational agent is going to pick the best of the actions. So the right thing to do then is to pick the best action here for A, and the max does exactly that, right? So yes, you can think of it as iterating over all possible action choices and then picking the highest of these sums when putting this equation together. All right. So like I said, this is the Bellman equation. And the thing you'll notice about it is this is no longer a linear system, right? So the max ruins things a bit for us. So we can't use just linear algebra to solve this. So our actually only recourse is using value iteration. So this dynamic programming approach we looked at for a Markov chain, where you compute a 0-step value, then a 1-step value, then a 2-step value, and so on. We can still do that here, even though we cannot solve this equation analytically because of the max. But this we can still do, right? So same deal as just a minute ago. Compute the value function v0 for all your state, then compute the value function v1 for all your states, and then keep going and keep going and keep going, right? And once we're done, so again, once this is converged satisfactorily, here is how we extract our policy once we have the optimal value function, right? So what is going on here? So what is this mouthful? So this is simply saying at any state, when my agent wants to decide what action to take, here's what the agent's going to do, right? So if I find myself in some state S, and the agent, or SI, I guess, and my agent is trying to figure out what action it should pick, it is going to consider all its choices, so A1, A2, and so on. And then for each of those successive states, right, we are going to consider the value of these successive states, right? And we are now going to take a weighted sum and discount it, right? So if I were to pick action A1, what is the weighted value I would receive in the potential successes of SI? Similarly, if I were to take action S2, what is the weighted sum of the values I can expect to receive in the future? So do it for all of them, and then take the argmax. So the argmax operator, if you're unfamiliar with it, is essentially saying pick the action that maximizes this. So it's different from the max, because the max says simply try to make this thing as big as possible. So that's going to give you a number, right? Some scalar. The argmax is going to give you the action that gives you the biggest quantity here. So the outcome of this argmax will actually be an action. It won't be a scalar, right? And this equation is saying, well, that's the action you should pick. Does that make sense? There was a question earlier in the chat, why did you say R is only a single equation? It's not a single equation, so I was referring to gamma. I was saying that is a single fixed scalar for the entire MDP. So we, ahead of time, we just are given this is the discount factor for this system, and we just use that in all of our equations. Right? Pi is a vector. Yes, you could think of pi as a vector, I suppose. So if you wanted to, you could write it out that way. So hang on, could it be a vector? Yeah, I suppose so. So if you just numbered your states 1 through n, And then the entries in the vector would be the action choices, right? So if you find yourself in state Si, look up that component of your vector, and that is the action to perform in that vector. Why did we replace V with pi? We didn't replace it so much as we solved for V first, and then we use V to solve for pi, because ultimately pi is what we care about, right? Because remember, the thing we're solving for is the policy. So what should my agent actually do in this world? And pi tells me that, right? V simply tells me what the value of every state is, which is useful, but that's not where we want to end up. Where we want to end up is what should I actually do in every state? So we first compute V and then use that to compute pi. So is the argmax choosing an action array out of many possible action arrays? No, it's choosing one action out of all possible actions that are possible in that state, right? So it's essentially saying, if I'm in state Si, I can perform many different actions. Pick the action that maximizes this expression. So where this expression you can think of as future rewards accumulated, right? So pick the action that maximizes my future rewards accumulated. That is the action I'm going to perform in this state. Yes, this is just for one step. So this is simply the action I will perform in this one state, right? Pi is not an operation. It's better to think of it as a function, right? So it maps. So pi tells you for every state, here is an action, right? So for every state, it tells me what to do. How do you fix a gamma? So if you are doing practical reinforcement learning, so you would pick gamma the way you pick every other hyperparameter. So try a bunch of values and find the one that works best, right? So how you would pick the learning rate, how you would pick any number of hyperparameters we have in these learning algorithms. Make sense? Other questions? Okay, so again, let's summarize this value iteration idea in pseudocode, right? So I've just taken the same equations and just put them in an algorithmic form. Basically, it's this idea of start with your initial guess at the value function and then repeatedly do this, right? So this is us computing those series of approximations. So start with V0 and then compute V1, V2, V3, so on. And again, I will claim without proof that this sequence will converge to V star, the optimal value function, right? And once we've done that, we extract the true policy, because ultimately at the end of the day, what is most useful to the agent is having some direction on how to act in a given state. So the value function doesn't give us that directly. So we need to perform this one additional step to extract the optimal policy from the optimal value function, right? Don't we all? So in response to the chat message, yeah. One thing you may be wondering is, why do this indirect step, right? So if the policy is, at the end of the day, the thing we care about, then why go through this hassle of first computing something else and extracting the policy as a side effect? So is there a way to just compute this policy directly without first having to estimate all the value functions? And this is actually a pretty important insight. It turns out that you can, and in fact, it's often a better idea to go directly to the policy if you can. So extract the policy directly rather than do this indirect step of first computing the value function. And the reason why this might be a good idea is, if you think about it, what we're doing here is saying, look one step ahead and then pick the state that looks, and pick the action that leads you to the best looking successor state effectively, right? But if that's what we're going to do after doing all this computation, you may realize, well, if that is all we're going to do, we're just trying to identify the best looking successor state. then maybe I don't need to compute these V star values very carefully, right? So I don't need to precisely know what the value of all my successive states is. I just need to quickly hone in and identify the best one. And that may be faster than waiting for, so the precise values of the states don't matter so much as getting the ordering right, right? I just need to know that state 5 is better than all the other states. I don't need to know that state 5 has the value, 200, whereas state S1 has -10, S2 has -3, and so on. I don't need to carefully compute all the values. I just need to know that 5 is better than the rest. So this insight leads us to an alternate way of solving for the policy, an algorithm known as policy iteration, which in practice ends up being far better to do. So you can prove that policy iteration will converge no slower than value iteration, precisely for the reason I just outlined, because all you need to converge on is the right ordering of your successive states. You don't need to converge on the true values of those successive states. So policy iteration takes a slightly different tack. It starts with a random policy. So for every state, I just tell you some action to perform at random. And then we're going to iteratively improve this policy. And the way we're going to improve the policy is by first, so we first fix the policy, right? So whatever current policy we have, we fix it. And remember, if I fix the policy, right, and I don't let the agent change its mind and I force it to follow this policy, we again have a Markov chain, right? Your agency, your agent has had its agency taken away. So it can't control events because if I freeze the policy, it has to do what it's told, which is again, just a Markov chain. And if I have a Markov chain, then I can compute the values of my states quickly. So this is the equation we already had before, where the actions are being dictated to me by my current policy, right? So what we will call the policy evaluation step. And we'll do this for a little while, allow this to stabilize. And once that happens, I will perform a policy improvement step, right? And in the policy improvement step, basically what we're doing is, based on the current policy, I induced some value function. And then based on this value function, I'm now going to improve my policy, right? So we interleave this value function computation with the policy update. And we just do that for a while. And when we're done, so this entire process will say that it has converged if my policy doesn't change from one iteration to the next. So if I had a series of action prescriptions at a given iteration, and on the next iteration after I do policy improvement, nothing changes, we have converged on a policy, so we'll call it a day. And we can prove that this algorithm will return an optimal policy for your given MDP, right? So I think we're at a little past 9, and I think this is a good place to pause. Well, actually, let's go one more slide into the future and then we'll pause. So just a quick recap. So we said, here is an MDP. This is a 5-tuple, right? And so far, we have been assuming that these things are known, right? That the transition model is known. So I understand the physics of the world I'm dropped in and how my actions, what consequences they have. And I'm also assuming that I know the reward function. And when all of this is known, we have an instance of what is known as an offline learning problem. So sometimes people also refer to this as a pure planning problem, where the goal of the agent is just to figure out how to act optimally. So, and since it has access to a model of the world, it can just kind of sit around and think in its head really hard, and sort of just come up with a fully formed policy and be done, right? The far more interesting case is when we are not given these things. So you are dropped in an environment where you don't know how the world works. So now you have an example of what's called an online learning problem. And this is precisely the scenario that reinforcement learning attempts to tackle. So what if, in addition to figuring out what I need to do in each state, I also need to figure out how the world behaves? So this is an example of a reinforcement learning setting. And the techniques we've developed so far aren't going to work, right? So value and policy iteration will not work because they rely on having access to the transition function and the reward function. So if we're not given that, then we need to look for other techniques. And that's what we will look at right after this break. All right, so I'm going to pause the recording now.